Hello everyone. In this video, we will be talking about the gram-schmidt orthogonalization process. What is this process? It's a process that converts a set of non-orthonormal vectors into a set of orthonormal vectors. So you might ask, what is orthonormal? The orthonormal come from the word orthogonal and normalization. So orthogonal, that means is perpendicular. So if a sets of vector are perpendicular to each other pairwise, each two of the vectors are perpendicular. That means the vectors are orthogonal to each other. And normal come from the word normalization. That means vector of length 1. Overall, orthonormal, popular orthonormal vectors such as I, J, and K in R3 are orthonormal vectors. Each of them is a basis vector length 1 and perpendicular to each other. Okay, this is what we aim to do, but each process should be similar to this. So first, suppose we have a vector set A that contains vector A0, A1 until A of n minus 1. So overall, there are n elements in this set, and each of the vector span all of them span all of n. That means each of the vector are linearly independent of each other. So if you think about linear independent, that means each of the vector generally point to different direction and span different space. Yeah, but there are more in-depth definition of linear independent that I will not be talking in this video. But first we have this vector. They are non-orthonormal, and then we want it to convert to set B that's contain orthonormal vectors, and that set B with the element B0, B1 until B of n minus 1. It should be perpendicular to each other, and the length should be 1, but it has the similar direction, similar to vector in the set A. That means B0 is similar to A0, B1 similar to A1, but B1 and B0 is perpendicular to each other. A0 and A1 might not be perpendicular to each other. So to do that, we can set B0 equal to A0. First vector, we don't have anything to care much. Can set it equal. But for the second vector, B1, it should be similar to A1, but it's perpendicular to B0. So B1 perpendicular to B0. In order to make it perpendicular, convert it into perpendicular vector, we can first we first take a vector and take away from the parallel component. So let me draw this for you. Suppose we have vector A0 right here and vector A1 right here. These two vectors are not orthogonal to each other. They are not perpendicular. In order to get another vector that is perpendicular to a0 but the same similar direction of a1, like for example this, so we can, for this we have two options, is to go up and to go down. Both is perpendicular, but we want the other vector that the endpoint of it is similar to endpoint of a1. It's the same endpoint as a1. So it's like it's this vector right here, or this vector right here. It's the same direction as a1. And to do that, we first project a1 onto a0, this vector right here. And then to get the perpendicular component, we can take a1 and subtract from the parallel component. So perpendicular component equal vector subtract parallel. I don't know how to spell parallel. Is take vector and subtract the parallel component to another vector. It's not parallel a1 but parallel to a0, parallel to the base. So we get perpendicular to a0. Okay, a1. So to get b1 is the blue vector. b1 is first take a1 and subtract it from the projection of a1 onto a0. That means the green vector right here. So green vector right here is the projection of a1 onto a0. And a0 is equal to b0. So we can replace a0 with b0. Get this. And that's the projection of a1 onto b0. Okay, and we can further expand more into this, because projection of vector we can write it as scalar product, scalar dot product between a1 and b0 all over the length b0 square, and finally times the because the projection of vector is a vector, so it has to, this constant right here is need to multiply with another vector in order to get vector. So that vector is b0, similar direction to b0 but the length is different. So that's why we got this right here. This is for b1. In order to get b2, let's think of it this way. b2 has direction similar to a2, but b2 must be perpendicular to b0 and b1. b2 must be perpendicular to both b0 and b1. In order to do that, we first have a2, right? So a2, we project a2 onto b0 and b1 to get a parallel component, and then we take a2 and subtract. After we project it, we take a2 and subtract it from the parallel component of both these vector, both the projection, and after we subtract it, we get the perpendicular component. So it's like this one. To get perpendicular, we take the vector and subtract the parallel. And what is the parallel? The parallel is just the projection. Okay, so we can write it similar to b1. We take b2 is equal to a2, vector a2, minus the parallel on the projection of a2 onto b1 projection like this, projection of a2 a2 onto b0 minus the projection of a2 onto b1. So in this case it's actually b0. I shouldn't have read it as b1, but we can think of it as b1. But a0, yeah, okay. Let's get back on track. We take the vector, subtract it from the parallel component. This one is parallel to b1, this parallel to this parallel to b0, this is parallel to b1. We take the vector and subtract two of that. We left with another vector that is perpendicular to both of them, both of b1 and b2. So it's like b2, and for b3 it's same case, but subtract another component that is parallel to b2. So similar. Finally we get bn minus 1 equal to a n minus 1. Subtract this, we can write it as a sum, or we can write it overall. So to write it all, we can write it like this. Project a, this I forgot, this is a2. So we check a of n, the vector a of n minus 1 onto b0, and subtract projection of a n minus 1 onto b1 and b2, and all until b of n minus 2, right? b of n minus 2, project a n minus 1. So this is overall the general way to write it, or we can write it as a summation. So bn minus 1, we can write it as b of n, something. It doesn't have to be bn minus 1. I want to write it because what we said in the beginning should be until b of n minus 1. So, but for b of n equal to a of n minus the sum sigma from for example j equals 0. J is like this one, 0. So j equals 0 until equal how many term is that? So this is 2 term. So it should be wait. Okay, it should be 2, right? Should be 2. Oh, it should be equal to the number of terms there are. So number of term is equal to the number of vector we add. So it's b2. We first subtract the parallel component of the first and the second. So b2 first and second, b3 first, second, and third. So this is up to n. The projection of a of n over b of j. A of n, b of j. Okay. Yeah. It should be something like this. but we can also explain it one more time by using the dot product. But this is not complete, right? This is not complete. In order to get a complete solution, we first have to we can what I said, to normalize it one by one. So after that we can normalize it. So in order to normalize this, we can first take the vector and multiply by the length, 1 minus length. So the length of vector right here is this mess right here, a of n minus, but I think we can expand it more if we really want, but it's the general idea. Projection of b of j times b a of n, project onto b of j. This is the length, and multiply it with the vector in order to get a normalized vector for each one of them. Multiply by the vector. The vector is a of n minus the sum from j to 0 until j equal to n of the projection of a of n onto b of j. Okay, so this is the complete one. If we write it, if we how do we say, if we did all the operation and then normalize it at the end. So if we find the orthogonal vectors and then normalize it at the end, it should look something like this. It should look something like this for general case of n equal 1, 2, 3. N equal 1. So this is actually not the correct one. The correct one, we should replace n with I or some number, because n we might confuse it with the n minus 1 right here. But generally n, for any number n, any natural number or integer n or I, can replace this with I. Yeah. So I think this is it, right? This is it. We also have some optimization if we normalize it after each step, meaning that for b0 and b1 we can normalize it here, and then for b2, if we refer to b1, it should make it easier to compute b2 if we know b1 is normalized. So it's another optimization that we can do, but generally this is the this is the general formula. In the next video I will be doing some real number example of this technique of orthonormalization. Yeah. Thank you for listening, and hope to see you soon. Bye.